Moving on from mining, the next part of the paper talks about Merkle trees. Okay, let's see what's the Merkle tree. Alright, this is a thing about the drawing, so the text begins here. An important scalability feature of Bitcoin is that the block is stored in a multi-level data structure. The hash of a block is actually only the hash of the block header, a roughly 200-byte piece of data that contains the timestamp, nonce, previous block hash, and the root hash of a data structure called the Merkle Tree, storing all transactions in the block. So the header is 200 bytes. I thought it was only 40 bytes now. Let me check that. Bitcoin block headers length size. Yeah, 80 bytes. I don't know why it says 200 bytes. Okay. It's not very important. It's just a bit surprising. Block headers. This is a so 4, 32, 32. That's what here. 32, 64, 68. Oh, this is 12. 12, 64, yeah, above. Sounds 80 sounds about reasonable. Okay, don't know why they say it's 200 bytes. Okay. A Merkle tree is a type of binary tree composed of a set of nodes with a large number of leaf nodes at the bottom of the tree containing the underlying data, a set of intermediate nodes where each node is the hash of its two children, and finally a single root node also formed from the hash of its two children, representing the top of the tree. The purpose of the Merkle tree is to allow the data in a block to be delivered piecemeal. A node can download only the header of a block from one source, the small part of the tree relevant to them from another source, and still be assured that all of the data is correct. The reason why this works is that hashes propagate upward. If a malicious user attempts to swap in a fake transaction into the bottom of a Merkle tree, this change will cause a change in the node above, and then a change in the node above that, finally changing the root of the tree and therefore the hash of the block, causing the protocol to register it as a completely different block, almost certainly with an invalid proof of work. Okay, so let's talk about this stuff. So what it says here is that when you are hashing the block to get the proof of work, to get a valid nonce for to show proof of work, you are not actually hashing the entire block. So the block, as we heard so before, contains contains a bunch of things and then transactions. So one could think that the block hash, is the hash of the entire block, containing all the transactions. That is not actually the case. The hash that you calculate for the data that you use for the block hash does not contain the transactions. It's only the header part. But in that header, you have what's called the Merkle Tree hash. And by including the Merkle Tree hash, this is as secure as hashing the entire transaction list. So this is what this is talking about. In what you would have is that, okay, this is the Merkle tree, and on the left and on the right is the Merkle tree that has a change. So let's start with the normal Merkle tree. So what you have at the bottom Okay, the tree is in computer science it's usually drawn upside down. So the root is at the top and the leaves is at the bottom. So the tree actually grows downward. Here we have all the transactions and they are leaves. So they didn't draw all of them, just drew one. But you can imagine that there are a bunch of them to the left and to the right of this guy. And then what you do is you take a transaction and you hash the content. So no more double SHA on the transaction content, and then you get this hash. So obviously this is just a portion of the hash. The hash is 256 bits, so it's way longer than that. For illustration, they just show the first 4 characters. And the way they are written in hexadecimal, so base 16. So that's why you have the digits 0 to 9, but you also have the letters 0 to F. That represents 16 different symbols. And in base 16, you need 16 symbols to have as digits between codes. Like in base 10, you have 10 symbols to represent the digits of base 10, radix 10. So the values here are not very important, and the exact value are not very important. But important to say is that they're all different, because hashes will give you different results if the content that you hash is different. So all these at the leaf, they will all be different. And then you start combining them. The trees start combining them 2 by 2. So let's say there are 2 here, they combine, 2 here, combine, 2 here, combine, and you have these 2 here. There are 2 transactions and they have 2 hashes. So you put one hash number after the other one. So for example, if these are the hashes, you will hash D1871235. So simply consider that the data that you put into the hashing function is the one hash followed by the second hash. And then you hash that and you get a result. And all these results are the one level up in the tree. So if you have a even number of these hashes here, then you will easily combine 2 by 2. And there will be no leftover. But if it's odd, what you would need to do to form the companion of this guy is to duplicate it. It's very simple. If for example we didn't have this node, we didn't have 1, 2, C5, and D187 was the last one, then you would hash D187 D187. You just repeat the same value. Then you have all hashes for one level up. So now we have E7 for B, and we have A8B5. So obviously, whenever you do that, you reduce the number of nodes by half. Then you repeat the process until you get to have a single node, and that single value will be the value that you will include in the block header, and that you will need to include in the data that has to be hashed to provide proof of work. So why is that more interesting than simply okay, this sounds very complicated compared to why do we not just hash the entire transaction? So we could put all the transactions in a row and then hash the entire thing. So why go through this particular step of creating a tree and making this data structure? So you actually have to calculate many more hashes than if you put all of them in a row. Right? If you put all of the transactions in a row and you hash it once, you only have to calculate one hash, and that would be extremely well, it would be much faster. We could argue that is this safer? Not necessary, but first let's see, is it even safe? So if we had all the transactions and we simply hash them all, obviously if somebody goes and then changes that transaction, So now, instead of sending from Alice to Bob, you say that the transaction goes send it to Eve. Then that transaction content will be different because the destination is a different address. Then the hash result will be a different value. So if we had this as a list of transactions, then obviously the hash of the list will be different. So we are safe against tampering. So protection against attackers, this kind of attack, is not the reason why they are using Merkle Tree. Right? So he didn't really say why he's doing all this stuff compared to just hashing the entire stuff, right? But we kind of see why if we see maybe he's talking about that. No, he didn't say about that. So let's see why. The reason why is that if you hover over this, it actually has SPV in Bitcoin. And it's a hint about why SPV. I don't remember what it is. Simplified Payment Verification, right? So this is what it stands for. I don't think the white paper explains what SPV is. Oh, here. No, sorry. All right, let's read the following section then. The Merkle Tree protocol is arguably essential to long-term sustainability. A full node in the Bitcoin network, one that stores and processes the entirety of every block, takes about 15 gigabytes of disk space in the Bitcoin network as of April 2014. Okay, that's way more now. In 2020, I think the blockchain has grown to 240 or 50 gigabytes. And it's growing by over a gigabyte per month. Currently, this is viable for some desktop computer and not phones, and later on in the future, only businesses and hobbyists will be able to participate. Yeah, because the blockchain never trims anything, and the UTXO state, the stuff that you need to use to verify transaction, is not published in the block or not. You have to derive it, calculate it from the transactions. So in order to, if you don't trust anybody with the UTXO sets, you would have UTXO set. You would have to download all the blockchain data and apply these transactions one by one. So that's why it's not for the. It will not be for everybody since it's already 240 gigabytes. A protocol known as Simplified Payment Verification (SPV) allows for another class of nodes to exist called light nodes, which download the block headers, verify the proof of work on the block headers, and then download only the branches associated with transactions that are relevant to them. This allows light nodes to determine with a strong guarantee of security what the status of any Bitcoin transaction and their current balance is, while downloading only a very small portion of the entire blockchain. Okay, so he didn't really explain how that works, but just the goal here. So the goal here is that, is that we would like to not have the entire blockchain downloaded. So we need to verify a transaction in a tree, right? So what you want is you want to request another source of data. So you don't want to download the blockchain. So you will ask a real node that has the blockchain and has the UTXO, so it has all the transactions, and you want to say, okay, well, I want to see that particular transaction because I know this is my transaction, or the transaction is for me. So you would want to, so you need to ask a third party, right? And the problem is that if you ask some guy, right, on the network, there is no guarantee that that node will not mislead you. It will not give you fake data. So you can't trust a node to be benevolent, and you need to verify that the data that was given to you is the correct one. So how would you do that? You would notice that if somebody goes and then changes the transaction, the hash will be different, and the hash of the header. So this is the part that you must verify, but that's only 80 bytes. I think he makes 200 bits actually, because 80 times 4 is no, so it would be 600. So I don't know. You can download the header. The header is not very big, right? And then you can hash the header and verify that the nonce and the proof of work is correct, and also that all the headers are chained. What you do not want to download, because you're a small node, is all the transactions. So compared to the headers, the transactions are much bigger. A block is about 1 megabyte of data, and only 80 bytes is in the header. So you can take the 80 bytes of the header, verify the proof of work, but now you may want to verify the transactions. So if all the transactions were hashed together to get the value that is put in the header, then in order for you to verify that there was no tampering, you would have to actually have a copy of all these transactions, including the one that of course you want, and then you recalculate the hash of all this stuff, and if it matches what's in the header, you say okay, it's a good one, right? Because nobody can change data it can change data and still get the same hash. So you can be assured that the data you got, since you hash it yourself and it matches the value that is inside the block header, that this data is the right data. Right? But the problem is, of course, that in order to do that, you will have to download the entire block. So that's not too bad if you want to just download a few blocks, but we can do better with this Merkle tree. Okay, stop scrolling for no reason. So what you would do, what you observe in this Merkle tree is that the data that you have on the branches, for example, if I have this node here, the Allison bomb, there's a path that goes to the top, and the path that is drawn in green. Right? You go to the parent, then to its parent until you reach the node. So that's the path, right? And that path, in order to calculate all these hashes, so all the way to the root, you actually don't need the data of the branches that your particular transaction is not part of. Right. So you see that these nodes in green have a sibling. So they always have one sibling, because we always combine two nodes together, or never three, and therefore there's always one sibling. So if I know the siblings, I can recalculate this hash. Right, so I do not actually need to know, for example, what's below D187. If you tell me D187, then I can calculate E74B, right? And then if you give me A8P5, I would be able to combine that with E74B and get DHCA, and so on and so forth, right? So the boxes in blue, they are not guessable, right? Because again, if you have a hash, for example, I have E74B, this is a hash, there's no way for anybody to guess D187. Right? So it's only by hashing D817 that I knew that the result would be E74B. Therefore, I know the association of D187 12C5 hashes to E74B. Right. So what happens if somebody tries to put a fake transaction, right? So now they put that transaction that goes to Eve, and that transaction hashes to 4A to F, right? So with the D1X7 that was known before, if we combine these together, we have now 94BC, right? And with 94BC, if I combine with A8B5, I would have a hash that is not going to be equal to D8CA, right? So that will be detected, right? So if you give a wrong transaction and all these siblings, you can see that you will hit a point where the hash will deviate, and then you will not have a match, and the transaction will be rejected. And you could argue that, oh well, why should I trust these D1X7, these sibling values, because they're also coming from that potential dishonest third party. The fact is that they have no other choice. I mean, if they give you another value, it would still not be good enough to match the tree, right? Because, for example, if they want to match E74B, like match on this node, then they would have to find another value here instead of D1X7. They would have to find another value, another hash, that combined with a 4A2F results in a hash of E74B. So basically, they know the target hash, and they need to find something that can hash to that value, and that's impossible, right? So already they can't do something about that, and therefore they would need to give something else, and then you will have a mismatch. If not at this point, because you could say that, okay, you're the guy, the dishonest guy is the one giving all these hashes, but he gives the green values as well as the blue values, right? So what about, okay, let's continue the line, and I give you D1X7, but now I say that the proper hash is 94BC. Okay, so you go and then you hash the wrong transaction, you get 4A2F, and you combine that with D1A7, you get 94BC, and you think, okay, that's what was told, right? And now you get the blue value, A8B5, you hash together, you get something, and again it matches whatever they give you, because they are still lying to you. They didn't give you D8CA, but they give you something that coincidentally hashes correctly. But eventually they want to get caught, because it goes all the way and then finally it reaches the top. So that top value would never gonna be 2F9C. It would be something else. And since that value is part of the block header, it will be hashed in the block header to be something different, and the proof of work will not match. The nonce will not match anymore. So this is how eventually the lie is uncovered. The truth is uncovered. Okay, so next step. So there's some flaws though, right? So you can prove that this transaction is valid, right? Because there's no way to cover the something that is wrong. But if you do not have the entire transaction tree, it will also be the node can lie by saying that a certain transaction never happened. So if, for example, you're searching for a transaction, they could say, no, this transaction doesn't exist, right? In which case, of course, they can't provide a proof that the tree does not have a particular transaction. So that's one of the weaknesses of SPV. You can prove that the validity of a transaction, but you cannot prove that there are not other transactions that are relevant to you, but the node refuses to return to you. For example, here, if you send it to Bob, but you also want to know that Bob has not spent it, it's not possible as far as I know with SPV. Okay, so the next section is alternative blockchain applications. Alright, so that's another section. I'm gonna pause here again. I think it's a good spot to stop.